Welcome to the Semi-Retired Podcast with your hosts, Richard Bonomo.
And me, Dave Farrant.
So Dave, this week we're talking astronomy, the science of the stars.
Not Johnny Depp.
That's a different kind of ass.
Yeah, right. Yeah.
So I guess if we're going to go science of the stars, astronomy, we should maybe quote Captain Kirk.
Why don't we?
Okay. My pants are too tight, Jim. What can you do?
I don't remember that.
That was one of the bloopers.
Oh, I see. Yeah, right, yeah.
So I guess space, the final frontier.
Space, the final frontier, yeah.
So when we talk astronomy, we're talking the study of planets, stars, moons, this kind of stuff, Dave?
Yeah, the root word aster, which is star, I think, in Greek or Latin. So we're talking stars.
And nomia, which means law, which so is...
Is it really? I thought it was... Oh, really?
I know. It's one of those weird things. Even the Latins can't get it right.
Good Lord. So it's the law
the
of
Latin
the stars.
Speakers, sorry. The Latin
speakers, yeah.
The old Romans, yeah.
So it's the law of the stars.
Yeah, and I'm guessing law meant something more like description
Must have been,
kind of thing. I don't think it's like law in the way that we interpret it today.
Right.
Otherwise, LA law would be a quite different thing.
Very different, yeah. So astronomy, basically, the study of the star. You know, in fact, in the word disaster, like a terrible event, is aster, the root word of star, with dis, it was like a falling star was seen as something that was as bad as things could get, a disaster.
Oh, interesting. I didn't know that. That makes sense. Back then, it would have been terrifying to see a ball of fire flying down. Today, we're like, whatever.
Yeah. Not a problem.
Depending where you live, obviously.
Yeah.
So we say stars, but we're also talking planets, galaxies, this kind of thing. So I guess we can define maybe a few of those things, right?
Let's start at the really big and come down to the more local. I mean, the overall term for all this material is the universe. It's the encapsulating space-time whatever bubble that everything exists in. And the basic inhabitant of the universe is the galaxy, of which there are apparently hundreds of billions, which have formed in the 13.8 billion years the universe has existed. So again, universe, basic inhabitant is the galaxies. The galaxies themselves are made up of stars. Again, depending on, I've seen different numbers, but I've seen like 100 billion stars per galaxy is a good average number. So that's kind of, 100 billion galaxies, 100 billion stars per galaxy. You start to get to some interesting numbers. And then down below that, you've got the planets, which are orbiting the various stars, like the planets, one of which we're sitting on right now, orbiting our star, the sun. And so it's a fairly simple structure, in that classification. Galaxies, stars, planets. Moons are similar to planets. They're, rocky bodies orbiting other rocky bodies, let's say.
They're like wannabe planets.
They're like,
groupies.
They are. They're wannabe planets.
They're the groupies of the astronomy
the
scene.
groupies of the astronomy world, yeah. Well, in a similar fashion, some of the planets, even in our solar system, are wannabe stars. I mean, Jupiter is a gas giant planet. Had it been much larger, had there been much more material, it could have had sufficient mass to cause sufficient gravity to collapse and ignite itself as a star.
Oh, really?
Yeah.
I didn't know that.
Yeah.
So stars, how's a star formed?
Well, it's formed from, let's look at the universe now. What is the universe composed of? And science tells us that all of the universe is composed of the same elements that we can identify here on Earth, the same 92 or 100 or so elements. Some of the heavier ones are radioactive. Everything from hydrogen and oxygen and nitrogen to gold and silver and tin and lead, all those things, they're all the elements. Science tells us that those are universal elements. They are everywhere. The simplest of the elements is hydrogen. One proton, one electron. Most of the matter in the universe, that's the stuff of the universe, is hydrogen. 75% of everything out there is hydrogen. Makes sense. It's the simplest. So you would expect to see a lot of it. The second simplest, or the second most abundant element in the universe, not surprisingly, is the second simplest element, which is helium. So two gases. That's another, I think it's 25%. The remaining 1% of all the matter is composed of all the stuff that we can touch and feel, like, the silver, the gold, like I meant, the tin, the lead, the aluminum, the boron, you think of all those names from high school chemistry class. All that stuff was cooked up in stars that eventually exploded and threw all that stuff out into space. So your star starts off as a bunch of gas that's swirling around and coalescing in a giant cloud. There's angular momentum as one of those basic concepts in the universe. Everything kind of has a little bit of spin to it. So you can imagine over millennia and billennia, if that's a thing, this cloud of gas starts to, hydrogen in this case, starts to kind of collapse under the weight of its own gravity. And at a certain point, there's sufficient pressure on the gas itself that the atoms of gas at the center of this ball fuse into helium. The hydrogen fuses into helium and releases energy as light and heat. This is the same reaction that powers the hydrogen bomb, which is a fusion bomb. So it's the same thing. It's atoms being forced together by gravity.
Aren't you giving away government secrets here?
Hey, I'm no Donald Trump, you know.
So when talking about stars, we talked a bit about the composition. When we look up, stars tend to be white, but we hear that stars can be multiple colors.
That's a very good point, actually. They do look white because our eyes, I mean, the light rays as they reach us are not strong enough to activate the color receptors in our eyes. But in fact, stars range in color based on their temperature. There's also a size factor there. Not all stars are created equal. You can get red stars, actual white stars. Think of red hot and white hot. Those are expressions we use thinking about stove elements, or a blue flame on an acetylene torch. There are blue stars and stars that are yellow like our sun. So there's a whole range. Again, we don't see them when we look up in the night sky, but if you look at stars through a telescope and see two stars very close together, these are called binary stars. And in fact, the majority of stars are binary stars. They pair up. Because there's a contrasting color in the telescope, you can pick up the colors. You'll see like an orange star next to a blue star, which is really quite pretty. And it's because they're so close to one another, your eye detects the difference. So yeah, they're not at all the same, a whole range. And again, it's based on temperature. Size is a big factor too. You know, you hear about red giants, white dwarfs, all this stuff. Mm-hmm. Again, you think of big stars, small stars. There's all kinds of them out there. It's a real menagerie.
So when we're talking stars and I mean, most people know our planets in our solar system. And our solar system is part of a galaxy known as the Milky Way.
The Milky Way. We came from the Romans. They called it the Via Lactea. In Roman terminology, a way or a via was a big road. You've heard of the Appian Way, probably. So when they looked up in the sky at night, absent all the light pollution that we have to deal with, they saw this Milky Way, they called it. It was like a milky luminescence of all these 100 billion stars, and they saw it as a road. So the Milky Way, that's our galaxy. That's where we live.
So our galaxy seems like, when you see it in photos, it seems to be like spread out, and it seems almost like two-dimensional, like a smear across the sky.
Yes.
I'm sure from space it would look very different. It wouldn't look flat and two-dimensional as we see it from here.
Yeah, you can think of our galaxy as a pizza with kind of a big blob of dough at the center, and we're out by the crust sort of thing looking towards the center when we look at the sky. So we see a long, flattish shape. If you were above our galaxy or below it, and with sufficient distance, it would appear like a big giant pinwheel, if you will, in the sky, because everything's revolving. The galaxies are revolving, the planets revolve, the moons revolve, everything's moving. You know, nothing's staying in place. It's all moving.
We're seeing it, you're saying, as if we're looking at from the edge of a pizza.
That's right. The edge toward the center of a pizza. Think about that.
And if we were above, we'd get something a little bit like what we saw from the James Webb, or that pinwheel galaxy, where that's maybe what we would see, something similar to that.
Yeah, and that's a beautiful one. If anybody hasn't seen that, have a look at the latest James Webb Space Telescope images. It's gorgeous. And yeah, something like a lot. There's different, I think there's like 6 or 7 different shapes. The galaxies come in. Some of them are just kind of big balls of stars, if you will, kind of so roundish. But very common is the spiral galaxy, where there's again, almost like wheels with spokes. How do we know that? Because from here we can see galaxies through our telescopes, and we know, and we've therefore inferred that ours is similar. And it's a very common type of galaxy, like our sun is a fairly common type of star. Nothing special going on here.
So it's possible also that as we're looking out, we could be missing some stuff because we're looking at the edge of the crust of the pizza, whereas in the James Webb, we happen to be in perfect alignment to see it from the top view down. And there may be somewhere we're catching just, not that space is flat, but in the sense of we're looking at the edge of the pizza.
Yeah, I mean, James Webb would do a better job of looking at the center of the pizza because it would resolve the stars to a higher extent. But what it's going to see more interesting is to look away from the pizza completely. The Milky Way, in that sense, is a blockage. There's that 100 billion stars kind of in your way, and there's dust and gas. There's dark lanes there. It's not all open. So if you point the James Webb or the Hubble away from that towards open space, that's when you start to see all these, like that, again, the first of the images that was released from James Webb was that deep field galaxy image. Hubble produced some of those as well. And it looks like there's 1,000, it's amazing when you 1,000 galaxies being visible in that image. And the most remarkable thing about that image is that the field of sky that it represents is equivalent to a grain of sand placed on your fingertip and held out at arm's length. So try that and imagine that in that tiny little space, you're seeing that many galaxies, each of which contain an average of 100 billion stars. It is literally unbelievably big. You can't even get your mind. I can't get your mind around it.
And if you can wrap your head around the size of the galaxy, there's always the other one, which is the other line, which is that the galaxy is ever expanding.
That's right. The universe is ever expanding. That's right. The universe is expanding all the time, and it's expanding the same. This was worked out actually by Edwin Hubble, I think, from the 1920s, so for whom the Hubble telescope was named. If you imagine the universe as a big basketball full of galaxies, the basketball is getting bigger, and everything in therefore is everything. All the galaxies therein, the base, the essential inhabitants of the universe, are becoming further apart.
Like my waistband.
And mine, for that matter. Yeah, yeah, it's exactly like that.
Exactly
like that.
That's how they show it in science class, right?
Sure.
So the Rolling Stones famously said 2,000 light years from home. What is a light year?
So in fact, they did.
Is that a year where you didn't work that much, or?
Yeah, I've had a couple of those recently. I know what you're talking about. A light year, a really light year.
2020 was a light year.
Yeah, it was a light year for everybody, I think. Yeah, that's so the light year is fundamental to getting a sense of how large the universe is. And the first thing to realize is that a light year is not an increment of time; it's an increment or a measure of distance. It's the distance that light travels in a year at its nice clip of 186,000 miles a second, 300,000 kilometers. So I can't even do the math. I've heard the number. But you can imagine if you were actually traveling in a car at 186,000 miles a second, how far you'd be away a year later. In fact, you'd be a light year away in this case. But the thing to remember when we talk about universal distances is that our galaxy, the Milky Way, is about 100,000 light years across. So it would take you 100,000 years at the speed of light to travel from one end to the other. And the Andromeda galaxy, our closest neighbor, is 2 million light years from us. And when you see these, updates on television about galaxies and James Webb, you'll hear them talk about 2 million light years from here, 160,000 light years away. You hear about stars that are close to us, but they're still like 79, 80, 100 light years away. Our closest neighbor star, that is, Proxima Centauri, is 4 light years away. So again, we get into that really fast car at 186,000 miles a second, and it takes us 4 years to get there. Hopefully, we've packed some snacks.
So we have our we're talking large, we're bringing it down. So we have, I guess, cosmology would be the study of the universe as a whole, as opposed to astronomy, which tends to deal more with the parts of it, right?
100% correct. Yeah, cosmology is the origin and the stuff of this, so the big picture. And yes, astronomy thinks stars, so a little more local.
So then, where does quantum mechanics fit into this?
Where does quantum mechanics fit in? Well, I mean, you go from the very big.
And is this something you learn in trade school?
Not that never having gone to trade school, I don't know. But yeah, it's quantum mechanics is the study of the very, very, very small. So what goes on at the atomic level and the subatomic level. So it's the other end of the spectrum.
It's like tiny universes.
It's like tiny universe, exactly. It's like tiny houses. You get tiny universes. Yeah, it's actually, I find it a very engaging topic. It reveals all kinds of what they call quantum weirdness in terms of what's going on at those subatomic scales that have no resemblance really to what we experience at the macro level. Even though we're made of this stuff, it's terrific. I encourage people to do a little research on that. It's a fascinating topic.
It's funny because when I think quantum mechanics, I always think of space, because quantum is close to quasars, which is a type of star, right?
Yes.
So I always put the two together, but they're like really opposite ends of the universe.
They're opposite ends of the spectrum, the very big to the very small. But having said that, I mean, all the stars are made of atoms, and atoms are made of quanta, or quantum mechanical elements or units. So it's all the same thing.
It's related. So the best way to look at the stars, obviously, the easiest way would be to walk out at night and look up and try to see what you're seeing there.
Absolutely.
You'll see those pinpricks of light up in the sky, depending where you live.
Yeah, depending where you live. And if you live near a big city like we do, and like a lot of people do, you've got a real challenge on your hands because of light pollution. In fact, there's only a few times in my life that I've been in a truly dark environment. I went canoeing the year after high school, way up north here, the Kabanga Reservoir it was called. And I just recall it being bloody well pitch black. And you're just not used to the blackness of it. There's nothing. That's if the moon's not up. If the moon's up, you can kind of see.
Yeah.
The other time was I went on a photography workshop out in New Brunswick, and it was, again, pitch dark. And at one point, we had to walk from the main house where the lecture was taking place down to our cabins. And it was a fairly long walk. Again, pitch dark, and you couldn't see the path in front of you. It was, we kept, I think somebody kept flicking on a lighter to give us, just to show us the next 10 feet so we could, because we didn't know where we were.
You didn't capture fireflies in a jar and use them
No,
as
we
a
didn't.
flashlight?
No.
Strap them to your head?
No, nothing like that. Yeah.
It's funny. My wife was asking me, we were looking up at the stars the other night, and she's like, where's the closest place we can go to see stars? So I went on, a dark sky finder, dark sight finder kind of, I figured it might take us to a different place. But like around here, one of the spots mentioned is Montmégantic, which has the big observatory up there.
Well, there you go.
And she's like, how far was that? I'm like, it's about 3 hours. It's about an hour, an hour and a half past Sherbrooke. And I said the easiest way would be a massive power failure.
Yes, it would actually. Yeah. Like imagine if we could go back during the ice storm.
Yeah.
Had I been thinking about it, and I wasn't at the time, which is odd because I got into astronomy years before that, that would have been a great time, not for anything else, obviously, but for looking up at the sky.
Yeah, it's funny that it wasn't a topic that came up. Like you think of the pandemic, there was a lot of studies talking about silence because there was no noise. There was big studies being conducted in the Arctic, dropping microphones into the ocean and being able to hear whales without the sound of ships.
No kidding.
Because there was an
that,
absence
really,
of shipping and sound.
Right.
So there was a lot of scientific research done that way, but we didn't hear anything about astronomy during the ice storm. Maybe it's because we were really caught in, some of us didn't have power.
Yeah, we're just really cold and hungry. And
like, who wants to go look at the stars in the middle of winter?
Yeah.
It's cold outside. It's cold inside.
Mind you, all the astronomy buffs must have been excited by that,
Exactly.
It happened during the war. I've read or heard sort of thing along the way that when there were blackouts during World War II, that, again, astronomy buffs were like, hey. I mean, even Los Angeles blacked out on a number of occasions because they feared attack from, I think, Japanese ships in the Pacific. So they would black out and all the, stargazers would roll out and go, wow, look at that. Because apparently, and I've never seen it, it's totally spectacular to see the Milky Way in a pitch black sky. Like, we just can't even imagine it. I mean, I've seen it in our light polluted skies in a darker part, but it's just a faint white smudge, and you've got to let your eyes dark adapt and go, oh yeah, I see it. You can sort of see it and you recognize some of the shapes from the photographs, but it's not like, spectacular. But if you were in the middle of Montmégantic, it would be a hell of a light show.
So as we're talking, looking up, we can you can see stars, you can see some of the constellations, right? Where we're drifting a little bit towards astrology here.
Who? Who? What? When? Where?
Yeah. Astrology, astronomy's geeky uncle.
Yeah, that's right.
Who makes things up and shows up in plaid.
Yes.
When it's not a holiday.
That's an excellent analogy. Yeah. The Herb Tarlick of astronomy.
The Herb Tarlick of science.
Science, yes.
Yeah. It's funny, the early Romans have a lot of talks about, the constellations, and then you have things like the Big Dipper and the Bear and stuff that are up there. And I don't know about you, Dave, but I've looked and it takes quite an imagination to see that is a pot of water or that is a someone hunting.
Yeah, I think they went out on a limb with some of those naming of the constellations, but they come down to us now and we're stuck with them. I mean, I'm an Aries, you're a
Cancer.
There you go.
That's what a lot of people say too about me.
Well, I've been called a ram too, so there you go.
That's not so bad. So I have an astrology related side note here.
Please.
My family has a lot of a few of the aunts were readers. They would do readings, right, with the cards and stuff. And one time we were having a party at our house, and both sides of the family were over, and my aunt was holding a grand séance in the spare room. Oh. And I remember sneaking over and listening in as she was reading the fortune of one of the other aunts. And basically, I overheard something and I ran out into the party and I screamed to one of my uncles, "You're going to have a baby! You're going to have a baby!" Because I overheard my aunt guessing that, divining that she was pregnant. Probably looked at her and could tell also.
Through the use of astrology, right?
Astrology, cards, divination, the whole...
Her expanding waistband?
I'm guessing, yeah, exactly. See, it all comes back to the expanding waistband. So the best way to get started is obviously just looking up, using maybe one of the apps like Star Walk.
Oh, they're so good. Yeah, I'm glad you mentioned that because there's great apps out there to help you kind of find your way, right, in a dark sky. Even a a semi-dark sky.
And then after that, we progressed to, I guess some people would try to use binoculars, but the binoculars are just not powerful enough. So,
well, look, I'll say actually, binoculars are good for certain purposes. What you're going to see, because really, if you get some with decent light gathering capability, when you think about binoculars, there's two numbers you see associated with them. One is the magnification. One is the second. So if you have 8 by 42 is very common. So magnification of 8 and 42 is the size of the lens. So that gives a sense of the binoculars' light gathering capability. Excellent for astronomy are the less common 8 by 50s. And so what that means is binoculars aren't good for looking at planets. They're certainly not any good for looking at galaxies, but they are nice for looking at star fields. So if you want to get a low, again, limited, but like really useful kind of tool in that sense. So, not to be overlooked, but certainly don't expect, too much out of them. Just, good, if you have a set, maybe if you got 8 by 42s or 7 by 30s, take them out. And have a look. You'll see something, but 850s do the job really nice.
Would you be able to see some of the craters on the moon with an 8 by 50, or do we have to move into your monsters? Your what is it, 15 by 50s?
Oh, those big ones that I have.
Yeah.
Even those.
With those, I think you can see the galaxy expanding.
So you can even see Uranus. That's the oldest astronomy joke in the book, right?
Exactly. We have to include it.
I have to include it. Yeah, I think it's a requirement. So yeah, I mean those are. I have a set of those larger. I think they're 15 by 80s or something. So again, that number of 80 you can see much larger than 50, and there's a geometric aspect to this. So it's actually like multiple times of light gathering capability. 15 times magnification, not 8. So to Richard's question, can you see some of the craters of the moon? A little bit again, but again, these are going to be really great for star fields. And there's a lot of what they call asterisms, where stars are grouped together that you can really see really nicely in binoculars. And they've got names like the coat hanger and I can't remember. There's lots of them. Really nice to scan with those binoculars and see those objects. But again, not going to see a lot of planetary views, not so much.
And the higher the magnification of the binocular, like for those in photography, the longer the lens. It's hard to hold it steady.
Oh yeah, that's a huge problem. Yeah. They've got to be on a tripod.
On a tripod, which brings us to the next instrument that's always on a tripod is the telescope.
The telescope. Well, there's
You rarely see anybody ever hand holding a telescope.
Not that I've ever seen. No, you'd have to be pretty steady to do that. Yeah.
Apart from those tiny telescopes that they use in the old on the ship. First mate, pass me my looking glass. And they'd pull out the little telescope and look out and look at the ships.
Yeah, that's right. You see Russell Crowe do that in Master and Commander, Far Side of the World, when he's looking for the French frigate that they're chasing, I think.
Exactly. So telescopes. So we get into the basic telescopes. You've got your small telescopes. When I was a kid, my brother had a little telescope, which allowed me to see pretty much nothing. But you move into the different types of telescopes. When you think of telescope, you think of a tube with lenses on the end.
Yep.
And so can you expound a little bit on the types of telescopes?
Sure. So what you've just described, the long tube with a glass lens at either end, which is what a lot of people think of when they think of telescopes, is called a refracting telescope. The word refraction, refers to how light arrays are captured and focused within the tube itself. And if somebody goes out and wants to buy sort of a hobbyist telescope, in a lot of cases, they'll come out with a refracting telescope. Refracting telescopes are great for planetary viewing. They're going to have a larger eye on them. Again, you'll get like a 3 or 4 or 5 inch refracting telescope. Those are, I think, 5 is large, but say a 4-inch refracting telescope is not that uncommon. So you've got a larger amount of light gathering capability, but you get the magnification now, because with telescopes, you can always flip out the eyepieces. That's where you look with your eye to achieve different magnifications. So you're on a tripod, so, reasonably steady. And I say reasonably because there's always wind and all kinds of other factors. And you can flip out the eyepieces and get a nice view of the beautiful views of the moon, high contrast. Sharp as a tack. The moon is terrific to look at, even though we kind of know it so well that it's really in our mental backyard. Looking at it through a telescope is always a little bit different, it seems to me, because you've got a one-on-one interaction with that object that is not the same as seeing it on in the context of a video or a photograph. You're really looking at it. And if you look at the moon on successive nights when the terminator, which is where the dark side and the light side meet, It's called The Terminator.
Just like the movie.
Just like the movie, exactly. Yeah, I'll be back. Is moving. Again, you begin to notice the change in light on the craters, and it's really, you get a sense of, man, this is a real place. So it's great for that. Looking at Jupiter and Saturn and Mars, Jupiter, Saturn, and Mars, I should say, great targets for a smallish telescope. With Mars, you can see, tonal variation. You're never going to see it like, kind of blood orange. It's never red, or blood red, if you will, like in the high quality photographs. Smaller telescopes just don't gather enough light to produce that vivid an image. But you can see tonal variations. You can see the ice caps. I've seen that. I've seen like bands across the bands of color. Or I think there's a large triangular feature on Mars whose name escapes me. You can sort of discern that. Jupiter is terrific. You can see the bands of color. There's the great spot, which is a huge storm. Like, again, it's a gas planet, so there's a huge swirling. It's called I think it's the great red spot. It's been there for like 300 years or something. You can see that. And what's really nice is you can see Jupiter's 4 largest moons, I should say, strung out in a necklace around the planet. That's spectacular. Because they're really level. They're really in a line. And you think, oh my God, like that again. You see the whole planetary system there because it is a planetary system. And if you're looking at the right time, and that right time will be published on on websites and in magazines, you can see one or more of those moons disappear behind Jupiter. So therefore, it's there now, and a minute later it's gone, or it's not there, and a minute later it's there. These are called the phenomena of the Galilean moons. It's got a big name for it, and that gives you a really visceral sense, an eyeball level sense of, man, stuff's going on out there. It's really nice to see.
And you can see all that with just a refracting telescope?
Yes, you can. Yeah, with a modestly sized refracting telescope, absolutely. I mean, I think even with the binoculars, you could probably discern some of Jupiter's brighter moons, maybe 2 or 3 of them. I think one is a bit bright, but in a small refractor or a reflecting telescope, which is the other one I'll get to, fantastic views. And we can't forget Saturn. I think both of us had an experience looking at Saturn through telescopes, if I'm not mistaken. Didn't you, when you were younger, look at Saturn through a telescope?
No. I was just describing the story of someone we know.
Okay, someone you know.
Yeah.
I did. It was kind of my start. I can recall going down the street one night, mid-'70s sort of thing, something like that. And neighbor, Stephen, down the road, had his telescope out. Never seen one, never gave it a thought. And he was looking at Saturn, which is, again, once you get into astronomy a little bit, you can recognize Saturn in the night sky. It's not like it's hard to find, nor is Jupiter, nor really is Mars. They're kind of obvious when you see them. Seeing Saturn is kind of mind-blowing because, we all know what it looks like. It's not like a shock. But when you see it with your own eyes and you see the little, beautiful little delicate rings around it, and in a small telescope, it might appear only white, or there might be a little bit of, creamy discoloration. Maybe you can see some of the divisions in the rings, but very faintly. You just go, my God, it's really out there. They're not making that stuff up. Not science fiction at all. It's really there.
Yeah, fascinating.
It's killer.
So we move on to the next type of telescope, which you said is
the reflecting telescope. Now these are going to be certainly maybe not what people have in mind when they think of a telescope, but they are actually the more common type of telescope, because as we get larger in the size of telescopes up to the big observatories, they're all based on light reflection off of a highly polished, slightly concave mirror. It's concave, right? When it's concave. Mm-hmm. You'll know you're looking at a Newtonian telescope if you see somebody looking into a kind of a rather wide, long tube. So it looks like a big cigar they're looking into, and they're looking in sideways from the top.
Yeah, so I always found that disconcerting. I'm like, why aren't you looking through the end of the telescope? They're looking through this little side piece.
Yeah, so what's going on there is the light, the telescope, the mirror, which is at the bottom of the telescope, at the bottom of that long, deep bucket, is collecting the light rays that are striking it. It's been ground in such a way as to reflect those light rays up so that they focus on a secondary mirror near the top of the telescope, and then they shoot out 90 degrees to the eyepiece. Again, where you can flip in and out your magnifications and focus and all that good stuff. So again, rather than with the refracting telescope, where the light rays come in the front and exit the back, there's a journey for these light rays. They come into the bucket, they hit the bottom of the bucket, they bounce back up to that secondary mirror. They're focused by the shape of that primary mirror down below, out the side, and take a look. What's great about reflecting telescopes is that it's easier, far, far, far easier to make large mirrors than it is to make large lenses. Also a lot cheaper. So now you get into like 6-inch telescopes and 8-inch telescopes and 10-inch telescopes and 12, 14, they call them light buckets at that point. Whereas the refractors, I really think they top out, if I'm not mistaken, around 4 inches. Okay. And that's an expensive refracting telescope. So reflectors, a lot cheaper. They're Newtonian reflectors, by the way. So, Isaac Newton came up with the idea. Bright guy, it seems.
Yeah.
And,
he got that after he got hit by an apple, right?
That's right. Yeah, exactly. Yeah, he got whacked on the head, on the noggin by an apple. And went, hey, hold on. I've got an idea here. So that's the reflectors, and even up to the James Webb, you'll hear them talking about its mirror, because it's got a giant mirror that's capturing those light rays like a big, big bucket, and reflecting them up to a secondary and over to whatever they got, whatever imaging system they've got going there.
And when we talk about telescopes and looking, we see often the observatories tend to be on mountains. You would think that if you want dark sky, no light pollution, why are we not putting these giant telescopes in a place where obviously there is no light pollution, like a desert, which is massive and has no light pollution? Why aren't we there instead of climbing to the top of the mountain?
Okay, that's a great question. So there's two factors there. One is the absence of light, as you just mentioned. The other is height above or into the atmosphere. Down at ground level, we're living in this blanket of gases that we breathe and exist in. The problem with those is that they interfere with the transmission of light rays as they reach the telescope. So by moving up in altitude, we move up through the atmosphere to the point where the atmosphere is a lot thinner, there's a lot less gas present. And so the image that's being captured, or that, the light rays that are landing on that big mirror in the light bucket, are not distorted in any way. We get a clearer picture.
So you want to get above the smog, the pollen, the pollution, or whatever is interfering.
Yes, okay. You want to be like as far above that as you can be. Yes,
and now we move into what I'll call space telescopes.
Yes,
you think of the Hubble, think of the James Webb, which are the two most famous ones. Although there were telescopes sent up in 1968 by the U.S. and in 71 by the Russians.
Well, I had no idea, really. That early?
Yeah. Apparently, the Orbiting Astronomical Observatory in 68 by the U.S. and the Orion 1 Ultraviolet Telescope. So ultraviolet.
That raises an interesting question. Yeah, sorry.
So what are we looking at? Why is there saying ultraviolet, and then sometimes you'll see an infrared telescope? Why are we not talking visible light here?
Okay, that's okay. So now we get into another aspect of this amazing story, which is we have to think of the electromagnetic spectrum, which I'm sure a lot of people have heard of, but maybe they're not sure what the different neighborhoods in the electromagnetic spectrum are. So within the electromagnetic spectrum, it is composed of waves of energy of different frequencies, from low frequency at the bottom to high frequency at the top. At the lower end of the electromagnetic spectrum, we have radio waves and microwaves. We know what radio waves are because they carry the signals we listen to on our radios. We know what microwaves are because they warm our food in microwave ovens. They're actually a type of light wave. Yeah.
So you get, so radio waves are kind of waves. So in the electromagnetic spectrum, you get sound and sight.
Yeah. It's all in there. And then as we move up a little further, we get infrared light. Now, I shouldn't have said light before, but electromagnetic waves. As we move up further, and as the further we go, the light waves are getting kind of more and more, the frequency is getting quicker and quicker. The energy is getting higher and higher. We get to infrared light, which is below the red, below the red. Think of infrastructure, same idea. Then we progress through the visible light spectrum. That's the stuff that we can see. And there's nothing special about those wavelengths. It's just that we can that they just our eyeballs can see in those spectra. Doesn't make them special. Just for us, they're special. Above that, we get to the ultraviolet part of the spectrum. So above the violet, below the red, above the violet. So now we're into slightly higher frequencies. And then above that are like gamma rays and X-rays and gamma rays, which are X-rays, which of course we're familiar from visiting the doctor's office, and gamma rays, which I think turned Bruce Banner into the Hulk, if I'm not mistaken. Seems to me. So, so it's all there.
So basically the Hulk is an astronomical phenomenon.
Aha, there you go. Yeah. Exactly. So back to the telescopes. I mean, the telescopes we use here on Earth, and any amateur has, are optical telescopes that we can, they process light within the visible spectrum actually, that's not true. They're gathering light in the other parts of the spectrum, but we don't see the light. We only see in the visible spectrum. So the interesting thing with some of the telescopes on Earth here and in space is they've been designed to see in the infrared or to see in the ultraviolet. I think that James Webb is visible and ultraviolet, if I'm not mistaken, or is it visible in infrared? And Hubble was visible and the other. So why do the designers do this? Is because there's really interesting, useful information in those parts of the electromagnetic spectrum that we can't see with our eyes, but they can be captured by digital sensors and turned into images that show us a lot of detail we wouldn't otherwise see. I hope that wasn't too roundabout.
No, that's fine. And then when you think of things like SETI, right, was those radio telescopes? Is that what we were trying to listen? You remember the whole SETI project?
Yeah.
Everybody was so excited back in the 90s, and you could download the SETI app.
That was
and you
could
help
search for extraterrestrial intelligence, right?
Exactly. You could download this and use your computer to help process the sounds or absence of sound.
I think,
or whatever. Those were radio sounds, right?
I think those were radio telescopes. So again, that's the other type of telescope. Again, within the electromagnetic spectrum, a lot of objects out in space emit in the radio portion of the electromagnetic spectrum, and some telescopes are designed to listen for or hear that part of the spectra. So yeah, and I think with SETI, there was a belief that if an alien civilization were broadcasting to us, we would pick up that broadcast in the radio spectrum. So yeah, SETI was, I think, very much focused on that. Yeah.
So space rock and roll. We were hoping
space rock and roll. Yeah.
Okay.
Yeah.
That's pretty wild. So from telescopes, we move into we got the space telescopes. Are there telescopes on the space station? Is there anything up there?
That's a good question. I don't know that there is, but I wouldn't be surprised to find out that there is either sort of thing. You would think they might have something as part of the ISIS, the International Space Station, but I don't know that for a fact. I mean, the only two I know are Hubble, which has been up since 1990, which we're talking about, and of course the new James Webb, which it's interesting to point out that also, whereas Hubble is in an Earth orbit. Again, I'm going to get this wrong, but I'll be close. Maybe it's orbiting 40 miles above the Earth, so way above the atmosphere, obviously, to your earlier point. But James Webb is up orbiting something like 1 million miles from the Earth. And this was done on purpose, I think, if I've heard this correctly, to shield it from any glare of the sun that, in other words, that might be shining in its direction and would blow out its sensor. Like almost if you pointed your camera at the sun, you don't get much of a photograph. Same thing with the James Webb and these other, you can't be pointing them near really bright objects. So I think it's in some kind of position that shields it to some extent from the light of the sun.
So not sunglasses then?
No, there's no sunglasses on these things.
Space sunglasses.
Although they did have to put eyeglasses on Hubble. If anybody recalls back in 1990, right. After it launched, it was discovered that Hubble had astigmatism, which I suffer from, so I know how bad that is. And they had to send a couple of dudes up in spacesuits to fix it.
Space optometrists?
Space optometrists. Yeah, exactly. But they did. They fixed it, and we got our images.
And so now this begs the question: if the James Webb is up there looking at the sky and looking at our galaxy, which the Milky Way, which you said we're kind of like on the crust of a pizza.
Yes.
Doesn't this kind of like prove the flat Earth theory?
Well, I'll have to think about that.
Or it would be the flat pizza theory.
The flat pizza theory of the universe. Yeah.
Something to think about, eh?
Well, look, I mean, science is nothing if it isn't about kind of, like exploring new avenues of information. Maybe we're onto something here. And now it's time for this week's rant. Richard, what's pissing you off?
What's pissing me off is light pollution in the house. Forget about the outside, street lights, car lights, crazy lights outside, UFOs maybe. What's pissing me off is the lights inside your house. You remember the old days? You got up in the middle of the night, you might see the VCR, you might see the microwave. Those were the first two sources of light pollution, unless you had a night light because, you stubbed your toes going to the bathroom. Now you walk out and you've got everything has a light on it. Everything from your power bars to your Wi-Fi routers to your hard drive. Your computer's asleep, yet it's still flashing, reminding you, I'm here, use me. There's lights everywhere. I walk out of my bedroom at night and I look down the stairs and it looks like I left all the lights on. I realize it's my stove. I got a new stove that's so bright it illuminates the entire room. It's like I got to put a tea towel over this so I can sleep. Well, how does this make sense? I got to cover my stove so I can sleep on the second floor.
You're making me nervous.
Enough with the lights. Can we go back to dark? We're supposed to sleep in the dark.
I was happy with it. I think John Lennon said, what do I see when I turn out the lights? I can't tell you, but I know it's mine. I think that's what he was getting at.
Yeah, well, I think if he opened his eyes, he'd scream. A bit like Yoko.
Maybe it was Yoko he saw when he turned out the light. I don't know.
All right, Dave, that was a good topic, and we'll put it to rest there.
Yeah, indeed. And thank you for the great questions, Richard.